Welcome to AP Podcast 10.9. This is on phase diagrams. And these are pretty interesting things, and students usually like this because they're pretty easy to understand. And basically what it is we take the temperature and we plot that. We plot the temperature versus the pressure, and you guys know that that has to do with phase, temperature, pressure, and then of course the intermolecular forces. And we look at a line to see where those changes occur. Now there's a couple of points I'm going to show you on the graph, but I want to get the definition down now. Critical temperature, that's the temperature above at which the vapor cannot be liquefied. And so it doesn't matter what the temperature is, you cannot turn it into a liquid. And then the critical pressure, that's the pressure required to liquefy it at the critical temperature. And that, last but not least, the critical point is where these two guys interact. And above the critical point is kind of interesting because you get a phase of matter that's not really a liquid or a gas. It's kind of both. So let's look at our first little graph here. Now here's a phase diagram, and this is the phase diagram for water. So it's kind of interesting. But there's a couple things that you need to know. Now I'm going to tell you the things that are important for like an AP test question or a Richardson test question. But the things you need to know about is where the phases are on a phase diagram. And it's always the same. The solids are over here. The liquids are always here. And the gases are over there. And if it turns out you forget where the gas is, well, look what's right there. Doesn't that look like a butt crack? Okay, so the butt crack's making the gas. I don't know, kind of silly way to remember it, but hey, it works. Okay, now this point right here is really cool because if you can get this stuff at this temperature, whatever it's going to be, and at this pressure, whatever it's going to be, I could just put 5 ATMs and I don't know, 75 degrees Celsius. This is not right, by the way. I'm just putting some numbers there. If you can get that material at that point, you will see all states of matter: the solid phase, the liquid phase, and the gas phase. And you've been around water when you've seen two of the phases, solid slash liquid or liquid slash gas, but you've probably never seen all three. And then right here is the critical point. Okay, going that way, of course, all the way to this point is the critical pressure that we just talked about. And right down here is the critical temperature. All right. So what occurs up here above the critical point? Well, this is where you can't distinguish a liquid or a gas from each other. So it's kind of a, I don't know if I don't want to go so far as saying it's a different state of matter, but it's a fluid. How about that? And that fluid is not a liquid and it's not a gas. So we'll leave it at that. So oftentimes in AP questions, they want to know where the triple point is. You're always going to look for that. You need to know it's where all three phases occur. And a better answer is that at what temperature and pressure all three phases occur. And then they ask you questions like, well, if we went from here to here, what would be happening in the state of matter? If we went from here and here, what would be happening in the state of matter? Okay, so let's try that because that's a common question that we see with these. So I've got some lines here. And if you would, pause the video, ask yourself what exactly would be happening for each one of these. And then we'll see if you get what I get. Okay, so going from this point, solid to a gas, we call that sublimation. And you've seen that in real life because you might see snow on the ground, it's a sunny day, and then you come back a few hours later and the snow has shrunk, but you don't see any liquid laying around. Okay? And what happens is you're getting this stuff going from a solid to a gas phase. Now the opposite of that is called deposition. Okay, and then let's see. If we go from B, now we've got our solid phase to liquid. So what's occurring here? Well, we're getting some melting, right? Okay, and in fact, if you want to think about it, this is the melting line, right? What would this line be called? What's happening right along this line? It's going from liquid to gas. Okay, that's the boiling point line. And then I guess Well, depending on if you're going this way or that way, that's freezing. Let's see, what's happening in C? We're, again, still going from solid to liquid, so we're still melting. Now, what's going on in D? We start here in the liquid phase, okay? Then we get above that. Look at this point right here. Here's our critical point. We get above that. So now we've gone, we're still in liquid phase, right? And there's no temperature you can get that to happen with that pressure. Then we go to that point where we make a fluid. You're above the critical point. And then after that, we go back down here and now we're a gas. So those are the kind of questions that you'll see. It's not too bad. Now there's one other thing that's really interesting about this curve, because this is water, and water, as you guys know, is very unique. The density of water is higher than in the solid state than it is in the liquid state. In other words, solids in water floats, right? You guys all know that. You've seen icebergs. Okay, so the solid floats, which is really unique. There's not too many substances that have that happen. And the way we can look at a phase diagram and tell if the solid would float or not is this line right here. Okay. Because another question that's often asked is, well, would this material sink or float in the solid state? And here's one for CO2. Okay. Now in CO2 we have this positive slope. But in water, very, very unique, you have this negative slope. Really, really unique, okay? So imagine I've got this thing, right? Now you guys know that the density of something equals the mass divided by the volume. All right? Now, with pressure and temperature, can I do anything with either of those? Well, we definitely can't change the mass, right? But couldn't I change the volume? I mean, think about it. If I have a gas and I put it under greater and greater pressure, greater and greater pressure, greater and greater pressure, isn't that going to change the volume? It is, isn't it? So it's going to cause that volume to get smaller, right? So as this gas goes up into the liquid state, the volume is going to get smaller, and that tells us that the liquid there, oops, pardon me for a second, that tells me the liquid here is going to be more dense, right? Which makes sense to us because we know that the liquids our gases are less dense than the liquid. Okay, now let's think about this. Let's say I've got this solid, right? And I'm right here at this, whatever this temperature happens to be, and I start jacking up the pressure. Goes up and up and up, and right here we start getting we get into that liquid phase, and then we get to this point. Now, as that pressure goes up, what's going to happen to the volume? Okay, the molecules are going to get squished together more, so the volume's going to go down, right? So if the volume goes down at this pressure way up here, right, and this temperature, now I've got a liquid that has a smaller volume per mass than the solid does. And so that makes its density greater than the solid, and therefore the solid will float. Kind of weird, kind of interesting. It's very unique. Okay, if we look at the other way, it doesn't matter where we go on this line because that positive slope, we can't get that point where we're going to get the solid to be less dense than the liquid. So I'm showing you that question because that pops up every so often. It's kind of a unique question. So let's look at a typical textbook question. And here we go. Indicate the phases present in the region labeled. Okay, so again, hopefully you'll look for the butt crack. There's the butt crack, right? So here's gas, here's liquid, here's solid. Okay. B says a sample of solid red phosphorus cannot be melted by heating the container open to the atmosphere. Explain why this is so. Well, let's look at that point. Where's the melting line on this thing? Because that's an interesting question. Right here is the melting line, right? And here's solid, right? So in order to get phosphorus to melt, it's got to go here somewhere at this temperature. But look at the pressure. Holy cow! All right, 43 atmospheres is way higher than what we're dealing with an open container, right? Open to the environment, which is going to be somewhere around 1 atmosphere. So the reason that can occur is because you don't get solid red phosphorus to melt unless you have a huge pressure. All right? And then let's look at the last one. Trace the phase changes that occurs when the pressure on a sample is reduced from point A to point B at constant pressure. Well, we're going from solid to liquid to gas. So there you go. Not too bad stuff, all right? So we'll play with a few of these diagrams and talk a little more about that density stuff later, and we'll see you next time.